Okay. The other way around, yes. Talk. Hello, hello, hello. Hello. Putting on. Hello.
Is it any better? Yes. There we go.
Okay. So welcome again. So let's continue with the talks. We have now Ricardo Ogando, and he will present his work on galaxy clusters hunters.
Yes. No animals will be hurt here. Okay. So, Madonna style. So let's talk about this thing, right? This galaxy clusters, which are the largest bound structures in the universe. And that's your general introduction to the subject. Let's just step back to how matter is distributed in space, taking a look at this beautiful image of a night sky in São Paulo. Of course, it's fantasy. It's a work by Thierry Cohen. If you wouldn't have light pollution in São Paulo, it would be great, right? This is what we would like. And so it's a sort of almost like what you see with your naked eye. And this, you can already see there are a few structures in the sky, right, in the universe. We are only seeing stars here. They are concentrated in the disk that now we know is the disk of our galaxy, the Milky Way. But to see more, to know further of the universe, we really had to, well, take pictures of it, right? And this really started to develop during the 90s, right? You had a few revolutions during the 90s. This is one of the first 2D maps of the universe, right? The APM Galaxy Survey. You use the photometric photographic plates that were scanned, and so you could build sort of map where you can already see some sort of structure here, there, or some overdensities, right? And take a hint what the matter distribution in the universe look like, right? The next step, and Brazil took some part on that, was to go 3D, right, with spectroscopy, where you can really tell the redshift of the galaxy. And so from the Hubble law, you know that the redshift gives you the distance, so you can build a 3D map of the universe. And one of the first maps was built by the CFA team here by Geller and Rucker, and also team up with the guys here in Brazil that use the OPG telescope, this nice green place here. They're 1.6 meters. They plug this sort of a spectrograph with a single slit solid state detector to really observe spectra here in the south. And so up there, it's working, sort of. Can you see it? So in the north part, you had this stick guy here, and it was one of the first time that you really looked into the structures of the universe. You saw walls and all. And in the south, you had this result here. So with spectrograph, you can really probe the universe, the structure of the universe in 3D. This was very sort of boring work because you had to go one galaxy per galaxy, right, observing one galaxy per time, and took a lot of time to have a sample of thousands of galaxies. Now you have, for instance, DESI, the spectrograph that will observe like 5,000 galaxies at once, right? So it feels like a wasted time, but it's part of development of the astronomy, right? So so the next step was really this sort of a multi-object of spectrograph using fibers, for instance. You had the 2DF and this LowInterest Sky Survey going deeper with a larger sample. And the other side of the revolution happened on the simulation side, right? So the resolution and the quality, the physics beneath what used to build the simulations also improved a lot, and this simulation would reproduce what you would observe in the universe in terms of structures, right? One consequence of having these larger samples of galaxies that you could start to try to understand, to slice it in different properties like luminosity, color, stellar mass, and have a better understanding of the universe, okay? Okay, thanks. It's, yeah, I think it's, yeah, well, I can see it better. So now that you are convinced that there is some structure in space, right? And gravity, from the beginning, we understand that gravity was the big player that was making this happen. Let's talk how to detect galaxy clusters, right? So George Abell was one of the first astronomers to really, with actually a magnifying glass, go through photographic plates and try to look for clusters of galaxies to build a large and sort of systematic, because he had a sort of an algorithm, manual algorithm, if you will, that he would look for galaxies within a certain magnitude range for a given redshift and build a list of clusters that we use up to this day, right? So this first catalog had almost 3,000 rich clusters up to redshift 0.2, and this was also sort of superseded by the technology with of digital imaging, right? This is actually from a small telescope, sort of an amateur image. So you with a CCD, a digital image, and of course several filters, you can build these deep images of the sky to look at clusters, right? So one thing besides the depth, I mean, you can see much more objects here than there, I guess. Also, you have the color, these images in color, and you can tell another interesting properties of the galaxy clusters that they are, in general, they have old galaxies, right? Old elliptical galaxies, and these guys are red. And this is a property that people will use to analyze galaxy catalogs and find galaxy clusters, okay? At the beginning, you had almost only a single passband image catalogs. You would have to use other techniques to find your clusters. After Abell, you had, for instance, matched filter, so where you would build a model of a galaxy cluster with a certain overdensity, a certain luminosity function, and build a likelihood, trying to match this model to the data, find peaks in likelihood, and that would allow you to find clusters. But once you had this colorful images with this sort of overdensity of red objects, it was this sort of the mainstream on finding galaxy clusters. Okay, of course, it's not only a matter of having digital images. This is just an example of how important it is to have telescopes with large field of views, right? If you give a public lecture, you often hear that the most questions are about black holes and or Hubble Space Telescope. Why don't you use Hubble Space Telescope to do that, right? And well, this is the field of view of the Advanced Camera for Survey of the HST, right? And you have to do a lot of pointings, right, to probe one cluster like the Coma cluster, right? So it's really important to have a large camera with a large field of view to probe the entire sky and see how the large-scale structure behaves, okay? All right. Of course, the next step on this digital imaging of the sky was this LowInterest Sky Survey, which made the largest digital image of the sky. These are the two galactic caps. It's a telescope in New Mexico observing the northern sky, and it's really amazing. It produced all sort of new science with it, and this is the next step, and to find optical clusters. But there are other ways to find clusters, right? For instance, cluster galaxies, they are, of course, overdensities of galaxies, right? But also inside this cluster, you have a lot of hot gas, right? A lot of hot gas over there, which you can observe in X-ray. And here is an image in X-ray. Also, this hot gas interacts with the CMB photos, right? Via the reverse Compton effect, and we'll have we'll produce the Sunyaev-Zodovich effect. So you can also observe in the submillimeter these galaxy clusters, and you have several projects to work on that, like the South Pole, the ACT, right? So you have several ways of finding a cluster. Probably the easiest one is by looking at the sky, right? Another way, and probably two-way, and many others will talk about that, right? Hello, is using weak lensing, right? You can view the sphere maps to map out the density of matter in the universe, and just to check it out, right? Of course you are, right? If you look at the images of the blue regions which are under densities, and images of the red regions which are over densities, you can really see the paucity or the over density of galaxies, right, in these regions. So the shear map, this density of matter in the universe is really awesome and probing the matter density in the universe. All right. Okay, so this is one way, but right. So talking about every way of finding a cluster will have a different selection function, right? So we have plenty of photos around in the optical. We know how to make image zip, and so this will make a difference on your final cluster catalog. So this is just showing a footprint, a spatial distribution around a region of the dark energy survey of cluster catalogs for the SPT, the Sunyaev-Zodovich, right? This is these white squares here. For the X-ray, these yellowish crosses here, or axes. And for WASP, which is an algorithm, an optical finder, cluster finding algorithm that I would talk in a second or in a minute, in red, which, well, you can never, in this plot, you can't tell the points apart because it's so dense. I mean, it's really an easy way to build a cluster, to find clusters of not only large clusters, rich clusters, but also small ones, right? So that's why you have a lot of guys around here in comparison to the X-ray or the Sunyaev-Zodovich, right? This will also reflect on the Redshift distribution, right? In the optical, will depend on the depth, essentially on the depth of your galaxy catalog, right? And we'll talk about the details of that ahead. The SPT has this interesting property of not depending much on redshift, right? So you can probe galaxy cluster far away, right? And the X-ray will really drop here really fast, and so you mostly find the rich ones at low redshift, right? In the meanwhile, the SPT will go far, and you'll find a lot of optical clusters. Okay, so back to the Sloan. Sloan was really the guy that started the business of having cluster catalogs with enough clusters so you could try to do cosmology, right? And it was a project that took a lot of years, and for each year you would make a data release, and with that data release you would produce a new cluster catalog, and you can see that evolution here. For instance, the papers of Christopher Miller in 2005, he reports around 700 clusters with a maximum redshift of 0.17. Then Benjamin Coaster in 2007, which was a sort of de facto cluster catalog for cosmology and everything else in Sloan, with 4,000 clusters and a redshift of 0.3. Then you have Van and Tal with 40,000 clusters. And each one of them, of course, the catalog was improving, was, up to 2009 or so, when you had the last data release of imaging. But also they were sort of improving the algorithm, or just pushing hard in the boundaries, going really into low richness clusters, right? Of course, if you go there, your uncertainties will be higher. And you have Zhang Gang Hao also with his catalog, and most of them will report to be very pure and complete, right? And this is sort of a joke, if you will, in the literature, I think, where everybody is like, oh, I'm 90 or 100% complete and pure, and if you compare each other, it's like they miss about 50% of each other cluster catalog, right? And so, but it's hard. It's hard. And then one of the things that you miss there is using a common set of simulations, for instance, where you know where things are, where halos are, right? And try to use these different algorithms with different selection functions to find these halos in the simulations and match them to see how you're behaving. So if you use different data sets, and it's hard to compare in the end, right? And one special algorithm, one of the latest, is the Redmapper, and it's being used a lot in dark energy survey, for instance. I think you will hear a lot here from Chuwei and Tong, right? It's and the key word here is the red sequence. Remember, I told you the galaxy cluster is essentially red, right? So they choose to use this red sequence to really enhance this overdensity detection and find their clusters, right? So it's a great algorithm. It's fast. It has high purity and completeness. It also has been focused on lower this mass proxy, their richness, right? The mass proxy scatter with a specter of other mass observers, and well, it has several advantages, right? So talking about this thing that's critical, right? If you are doing a cluster catalog, an optical cluster catalog, you just count galaxies, right? A cluster is made of galaxies, and then you count galaxies. A richer cluster will have more galaxies. A poor cluster will have less galaxies, right? But you can match it to other observations. For instance, weak lensing, or the SPT, or the Sunev's Observatório or X-ray, which give you some sort of another mass indicator, and try richness behave, right? And the plan, the aim here is to try to reduce this scatter or try to understand how this richness behave with the mass. All right. So as I told you, most of the things has been happening on the realm of this dark energy survey, right? It's a great project by itself, and also it's being considered a sort of precursor of LSST. It has this funny footprint in the southern hemisphere, trying to connect with the equator with this Lowell digital sky survey that was around here, right? So you can compare figures. It has a region that overlaps with the South Pole telescope, so you can try to compare our cluster with their clusters, right? It's been originally a 5 years project, 6 years that we'll finish observing in next January, in a couple of weeks. We just had a collaboration meeting a couple of weeks ago at Unicamp here. Some of the guys were here, others weren't. You missed. It's producing a lot of nice scientific results, right? So just to highlight, that's using a 4-meter telescope, right? It has this almost 500 megapixel camera detector with a sort of a almost 3 square degree field of view. It's 14 full moons in the sky. It's a large area. It's covering a 5,000 square degree. It's also trying to escape the Milky Way, which is here, right? That's why the footprint. Right. This is a table, boring table from this paper by Alex Trilka, which tells you which gives you the details of the first galaxy, of the first objects catalog for DES from year 1, right? And you can see that you had a good scene in average. That's related to the turbulence of the atmosphere, right? We'll measure the crispness of your image, and then the ability to measure shapes and measurements in weak lensing. The magnitude limits relate to the depth of the survey. Where is that? It's here. So you want less of that and more of that, right? So go deeper and with sharp images. And of course, with LSST, all of these almost 5 years of work will cover in a couple of weeks. You have an 8-meter telescope, a larger camera, more sensitive, and well, a different survey strategy. But well, such is life. So that's the sort. That's to give you the sort of impact that LSST will make in looking into the sky and observing the sky, right? So we really build this high definition or ultra high definition, I don't know where we are these days, of a movie of the sky, okay? Just to give you a bit of the dirty details of before getting to this nice cluster catalogs. So you have the observations here, the DCAM observations. The CAM is the dark energy camera that was built for DES. You reduce the image. You need to do photometric calibration, right? Because the photos they get into your telescope and instrument, and they go out as a number that you need to make some physical sense out of it, and so you need some photometric calibration. You make an image, but you can also revisit that region of the sky again later, right? This is the survey strategy. You make several tilings, several layers of image of the sky. This helps you with several observational effects, and also allows you to co-add these images, stack them. And what the final result is to have a higher signal-to-noise image, which will be deeper, right? And with this co-added image, you can do the so-called source extraction, which is actually to measure the stars and galaxies in the image, right? And their brightness, their shape, and produce a catalog. And then you can go further. You can tell apart who are stars, who are galaxies, measure their redshift, and build some ancillary maps that I'm going to talk about right now. So these ancillary maps are a critical part if you are trying to analyze a galaxy catalog, right? So as I told you, we have several layers of observation, and the CCDs, the mosaic of the CAM, which we are just seeing a section here, right? They have gaps, and the field of views are in the wide survey. They are not exactly one of each other, and that's on purpose because you want to cover the gaps also, right? But you have some sort of variable depth across the entire footprint, right? And you need to track that. Why? For instance, if you're looking for galaxy cluster, right, or analyzing the large-scale structure, and you're seeing more galaxies over there than here, and you think it's a cluster or think it's some structure, right? You need to understand how this depth changes across the sky, so you don't mistake structure with depth, right? That's why you have to track these sort of things. And this happened this starts with this thing called Mango maps. It's a high resolution maps that you, well, it's for most of the analysis, it's very hard to deal with. So people sort of degrade them. We're using HeoPix maps. I think most of you have heard of HeoPix. It's a way of pixelizing the sky. You can have different sizes of the pixels. These are equal area pixels. And so you can translate these properties, these observational properties across the footprint into maps and put them to your analysis, right? So just an example of a map of the survey depth measure for galaxies, right? If you measure, so most of the DS science is focused on distant galaxies, right? But there are a few guys that are interested in stars. There is a lot of Milky Way science as well. So the way you measure the depth for stars and galaxies is different, right? The galaxies have different shapes. So if a star is just essentially a dot, right? So that will reflect on how your error, your brightness, your magnitude, or which translates into brightness, right? Error changes with the brightness of the object, right? And so you can use that to build these depth maps, which give you how deep you're observing that region in the sky. Okay, so that's for year one release. Okay, so that's why it's incomplete. Now we have the full footprint complete. The star galaxy separations, I said, you can separate the stars from galaxies. You can see here a bit of the Milky Way invading the footprint, the GS footprint, right? This is overdense of stars here, right? You want to get rid of them. And this is the nice and sort of homogeneous anisotropic galaxy distribution, except for some depth variation. And so just to give you a bit more details on this, I think it's interesting, right? We here in Brazil have a call, right? If you look close enough, nobody's normal. If you look at the galaxy at far enough, there will be a point you can confuse it with a star, right? And so it's very easy to tell apart this galaxy from the star here, but if you look at the small dots here in this image, your life gets complicated. And so you cannot use just shape to separate them. And you start using different things like machine learning because these guys will have different colors, for instance, of the galaxies will have different colors of stars. So in this multi-dimensional space, you can fit them. And so that's when HST comes to act, for instance, because since HST is outside of the atmosphere, is not influenced by this turbulence which degrades the image. So you can use it as a sort of a truth table, right? You can really look at deep images of the sky and tell stars apart from galaxies and use it as a truth sample for your training and do some star-galaxy separation, right? This machine learning method also used a lot to measure photometric. Redshifts are critical to these 3D maps of the universe, but to do spectroscopy is very expensive. So the way to do is to do photometry in different bands, right? But then it will be very coarse, and you have different ways of measuring it, either by fitting a template to this, or by matching your photometry to known spectroscopy and building sort of a training set, so you can apply machine learning algorithms to tell how a photometry of a given object translates into a redshift. Okay, so all of these products, right, can be the maps, the star-galaxy separation, the redshifts. They can be joined in in a system that is been one of the most things we've been working at this LIneA, that's a laboratory that I work at, which it joins in a smart way and in a way that allows any scientist. So I'm a Milky Way scientist, I'm an extragalactic guy. If you want to do different kinds of sciences, you can choose different kinds of selection of your maps and star galaxy separation or photometric redshift algorithms, and join them in an efficient way in a database and produce a value-added catalog, or the catalog that you're going to use to do your science. Okay, this has been recently published in the Faust Neto 2018. Right. So let me finally talk to you about this WASP, or WhatsApp, it depends who you talk to, which is this Wavelet Zee photometric cluster finder, right? So it's a 2D plus 1D. You will slice, you build 2D wavelet maps, I mean, in a way to show the overdensities, right? You do it in slices. This is just an example, and Z3.5, and you can see here, the overdensities is larger here, so you would say that the redshift of this cluster is 0.35, right? And the one thing that's different from the Redmapper, for instance, that we talked earlier, it uses the Z to manage this projection effect instead of the red sequence, right? The red sequence evolves with Redshift, and you can use it to track the cluster across Redshift, or you can use directly the Photometry Redshift. The allegedly advantages of that is that you can probe higher Z clusters and sort of a bluish clusters, right? Cluster of a galaxy is not red. It can happen to the best of them. You would find it, right? So just to tell you a bit more, this is the color versus mass for some galaxies. You can see the red sequence here evolving as a function of redshift, right? So as you go deeper, as you see a younger universe, right, you start to miss these older galaxies, and so in principle, you could start to miss your power to find clusters, right? Of course, you can go to radar bands to try to probe that at higher redshift. Okay. Of course, I won't try to say to you that it's photometric redshifts much better than red sequence, right? I won't try to deceive you. Of course, it has also difficulties, right? You have to understand the bias, right? Here's a Z-spec against the Z-thought. You understand the bias and also how the error behaves as a function redshift in order to not misplace your cluster, right? And so having that work in a nice way, it's also hard. Right, so clusters. Nice pictures of clusters. So we have here richness versus redshift for a few clusters found by WASP, right? We have this science portal which is integrated to a target viewer. So we produce this cluster catalog, and so you can just eyeball them right away, right? And so you have some rich cluster of galaxies here, one nearby, one far away. Poorer, and well, good luck with that. A poor high redshift cluster. This is a very good screen, by the way. Congrats. So you can really tell them, you can really see the difference by eye and how, and you can really see how hard it is to find distant clusters, poor clusters especially. Okay. And then we use that system to eyeball and verify, validate the findings, right? Okay, but then eyeballing is not enough. You need to check how good is your cluster catalog, right? And the first approach is to do some matching by proximity. That means if a cluster in both catalogs have the same X, Y, and Z position, right, let's say, right? that would give you a match, but then there is an issue, right? Function of cluster of galaxies, you have much more lower galaxy cluster mass galaxy clusters, so you have a high probability of having lots of small clusters near your cluster and have a mismatch. So you also have to rank by mass, or to rank by some sort of mass proxy to have a proper match. All right. So these are a few examples of the WASP catalog matched to the SPT cluster by Bling et al. So this is completeness as a function of Redshift, thanks to Michel Agana here. I stole from his talk 2 weeks ago at the ES meeting. So you have a high completeness here. So this once again, we are matching the WASP catalog to the SPT catalog and checking how it behaves as a function of different richness or mass proxy, right? So it matches most of them up to a point and then start to lose. Of course, this is related to the magnitude limit of the galaxy catalog that we are using. There is some sort of a bias here in the redshift, but you can understand that bias. I mean, you can measure that. We also try to match to the Redmapper catalog, which is the favorite, right, in the collaboration, and then reproduce quite well the results for the most massive objects. So there are 2 versions of the catalog. These are that very poor that we talked about, but that you should be aware of. So I wouldn't mind just sticking with these guys here. And also the redshift behaves quite well. All right. So if you are happy with your cluster catalog, you can try to answer several questions, right? How galaxies forming to these clusters into the clusters and outside in the field behave, how they evolve. This involves several physical phenomena, right? The gas cooling, the star formation, the feedback from active galactic nuclei or supernova, right? Of course, main thing here is to understand cosmology, right? Is it lambda? Is it dark energy? Is it multiplied gravity? And the key thing that will be addressed here, the mass measurement. This is the key thing to try to get into cosmology, right? You really need to understand how the mass is measured for the galaxy clusters, and who know to understand the dark matter properties. I think I'll have to run a bit, right? How many? 10? Ah, that's okay then. So here you have some sort of stranger things, right? Where you have the upside down world. You have 2 dimensions, right? You have what we call the real world with cluster of galaxies and the halo world, right? World of the realm of the simulations, and so they use the simulations to understand the physics of the real world, but you need to connect them, right? And it's hard because galaxy formation, for instance, there is a lot of things that you cannot understand by doing simulations, as we'll see here, right? So as I told here, there are 2 approaches to try to connect the observing world and the simulated world. Empirical modeling. Joe the Rose will be here, right? No? But Joe the Rose? Yeah? Okay, but we'll probably talk about at Gauss and all. Okay, cool. So the empirical modeling, you can get, you observe the world, you try to model it, get your understanding for the world and you put back into the simulations, or you can try to simulate from first principles, which is very hard. So just to show, there is this nice graphics here from Wexler and Tinker. This is a recent review. So if you want to simulate everything from first principle, very expensive, but of course more predictive. But if you go here and produce your mock catalogs from some assumed knowledge of the universe, right? You see how the colors or the luminosity function behaves with the clustering, and you apply that to your to build your mock catalogs based on, for instance, a halo catalogs that came from an in-body simulation, but doesn't tell you anything about galaxy formation, right? So this will be less expensive, but of course less predictive. But it's very helpful anyway. And then comes the question, what's a halo, right? This is the parallel of the galaxy cluster in the simulations, is the basic unit of our large-scale structure. So it's essentially an overdensity that is defined by this formula here, where you can choose exchange VDL here by 200, for instance, if you're measuring the mass for a region of 200, the mean overdensity of the universe. Okay, but there is, just to address something that I think will be presented here elsewhere, there is an issue with this definition. This and sizes of clusters are key definitions, right? But there is an issue with this definition, which is that the critical density here that you use to scale this, to define this cluster, it evolves with time. Here you have the critical density as a function of redshift, so it gets lesser and lesser with redshift, right? And what gives you is that you have this sort of pseudo evolution, right? If you start with a given mass and radius at a redshift, since your reference critical density is changing, will change your mass and size of your cluster, give you a sense that there was some sort of evolution or mass accretion when there was not, and will mislead you. So this is being called the pseudo-evolution, and it was proposed a new way to measure size of clusters, which is the splashback radius. Chiwei will talk everything about it. No? Okay. So the splashback radius, it's a radius that in the simulation separates it tells you about the first infall of material into the cluster, of a galaxy into a cluster, right? And since it's this radius that's tracking when a first galaxy gets into a cluster, it's really telling you about mass accretion. Right, it's a really good way of tracking the evolution of the cluster. This is just to compare how the splashback here in this gray light here compares to the visual radius for different halos in the simulation. And what can I do with this splashback? So you can, of course, assess the accretion rate of halos. You can verify if different populations have different splashback radius, right? A blue population, a red population. That's being presented, and Shin et al. It's read on the archive. Can you measure on non-luminous matter using a weak lensing, for instance, right? And compare to what you measured with galaxies. If you measure the profile densities of galaxies and see if there is a splashback there. And of course, with a proper sample, a deep sample, you can try to see if there is an evolution of these radius or NR of the population with redshift. Okay, so this sort of splashback radius is really on the news lately, right? So the next great thing, important thing is to weight galaxy clusters. Anyone's missing the reference here? So our dear Indiana Jones here is trying to assess the weight of this little statue here, so he doesn't get in trouble with the traps from this ancient people here. So he will try to calibrate the mass of the cluster, right? And of course, you know how it ends. Well, it ends in trouble with a big ball rolling over himself, right? Over him. Because just like for Indiana, it's hard to measure the mass of this cluster, right? Yeah, he didn't measure it, right? Beware, son, you might get in trouble. Right. So there has been a lot of effort inside DS, for instance, to study how the mass behave with richness. There is a Sato et al. Papers for science verification for U1, Tone using the weak lens and also address this subject. And now I'll let him do his thing. So just to close and get to the point about LSST, I mean, most of the things that I've shown here are quite interesting and have been doing by DS and with a lot of effort from a lot of people during several years. But LSST, I mean, this thing will really jump to another level, right? You have billions of objects, right? You have around 300 million galaxies in DS with hundreds of thousands of clusters, and this will really jump for LSST. We really get really deeper, right? In a couple of weeks. So this is just one of our final slides, a motivating slide to really tell you how big LSST is on this thing. So we'll be the largest optical galaxy cluster sample ever. We'll have better photometry that for your photometric redshift, your weak lensing, your macro-axis. You have follow-up surveys around during when LSST is online, like Euclid, Rosita. So that's it. Who wear it better?
Thank you so much. Do you have any questions?
So I didn't quite understand how WASP works. From what I got, it's that you're analyzing the cluster on the redshift space, right?
Which work are you?
So when you present WASP at first.
All right.
Right there. So that's the same cluster, right?
Yeah, that's the same cluster.
But from what I get from that is that you'd need like a spectral cube to do that analysis, right?
Sorry, I didn't get it.
You'd need like a spectral cube to do that analysis, wouldn't you? Or
well, so with photometry, if you have enough bands, you can measure sort of a redshift, right? That's what is in here, right?
Okay. So in that case, the different redshifts would be just different bands.
So you can track. So you can see this. This is the same spectra displayed in redshift, right? So and if you convolute the passband with the spectra, right, this will translate in different bands on each band. So for instance, for this blue guy here, you will measure a large. You have some flux here, right? If when this guy goes over here to a higher redshift, the flux here is lower. The flux of the galaxy is lower. So, and the same for this band, right? So as the on the spectra, right? This will change the shape of. Oh dear. This will change the shape of your spectra, right? The measurement of the flux of the galaxy in the different passbands, right? And that's how you try to assess this photometric redshift, right?
So in the previous image, so each different redshift is just a different band.
No, you use all bands to understand the distribution of flux, right? And sort of build a spectra, and build a spectrum, right?
Yeah, thank you.
So how cosmological parameters change if you make the analysis with this splashback radius? Is there any change, or is it essentially the same?
I don't think the splashback get in the current analysis. So what you use is the mass function. Of course, if you change the way to find the mass, But one way is to measure the shear maps, right? For DS, you've been doing that. Measure from the mass from weak lensing, for instance, right? Well, Chue can comment or Ton. I don't think that it has any effect currently on the analysis.
That's a good question, and as a matter of fact, the answer right now is kind of that we don't know, and it's because the theory, like the theoretical framework behind using splashback radii isn't really developed yet. For technical reasons, it's kind of hard to measure in simulations.
So you cannot get a mass function with this kind of definition yet.
Oh, you can. It's just hard enough to the point where no one has done it.
So yeah, so let's try to tell if you try to, for instance, try to track, if you define as the info of a galaxy into a halo or a point into a simulation, it's hard to track every point, for instance, to see when there was the first info and see how there are other techniques, but as Tom said, it's hard.
I think that is one of the motivations in the beginning why they want to get develop this radius is just because it has a more physical meaning than just defining R200. So that's the motivation, but as Tom said, there's a lot of practical problems.
You mentioned that the new method, WASP, could eventually detect bluish clusters. Did you find any evidence that there could be an important number of them?
So yeah, so there is a collaborative work first. So following this, there are several ways of finding clusters, right, with different selection functions. And for instance, if you go to the X-ray, if you use the X-ray to go and look for galaxy clusters in the optical, so the other way around, instead of going from the optical to the X-ray, you go from the X-ray to the optical, you can find things that you were missing here in the optical. And why? Because they are bluish. It's not the rule, it's not, but it happens.
Do we have any more questions? Well, I have one coming back to the the Halo finders, right?
Sorry there.
The clustering finder.
Okay.
I consider it's okay from the simulations. Actually, you, as far as I know, I'm not an expert, but what I heard is that okay. So you have somebody simulations, and then what you have to do is just to realize the velocities of these mass particles and realize whether it belongs to a bound object or it's just passing by. Right? This is the big issue but from the simulation point of view. But then from the observational point of view, because as far as I understood from the WhatsApp WASP, it's that okay, you use photometric to infer somehow a spectroscopy. Let's just say, okay, which redshift this cluster was. But how do you know at the beginning that the object you're looking at is the cluster itself or something else? This, I mean.
What do you mean by the beginning?
I mean, okay.
So,
I mean, okay. You see, maybe stupid question. So you see a bunch of stuff, not a bunch of galaxies there, and then you say, okay, this bunch of galaxies that I see, they belong more or less to the.
Yeah, so that's an interesting question. So for one thing, you can also assign sort of a membership probability. So a galaxy it's not 100% bound to that cluster. It can be 90, 80, and if it's, I don't know, in the outskirts, 10, 20, and could have a probability of belonging to two halos, for instance, or two clusters, for instance, right? So you can assign a probability, a membership probability. So that's one thing. That's right. So it's hard to tell the boundary of a cluster, right? To say, oh, it ends here and it belongs here. Don't go there, right? It's a nebulous thing, right? The other thing, so besides that red sequence, one thing that people have as a seed of a cluster is the brightest galaxy in the where is that? Yeah, so imagine this is a cluster and in its red sequence, you have the brightest galaxy there in the cluster, this will happen to be the seed. The algorithm will go there, will find that guy, and look around for members, right? And so this is one thing, right?
So you assume that the brightest is like
Yeah.
more
So
or less stays
in
the same.
general, yeah. In general, there is of course some miscentering, right? The universe. Sorry. That's how one of some algorithms work, right? They go for this brightest galaxy as a seed. But if you just build these 2D maps of overdensities, you go there and tell this overdensity is a cluster, right?
Okay, the Redshift for sure helps defining whether it's a cluster or not. No?
Well, helps in terms of the projection effect, right? In slicing the universe. But one thing that people often ask is, I mean, oh my word, that is 0.45 and 0.25. This is a huge cluster, right? It's going across the entire universe. But I mean, that's how coarse the photometric redshift is, right? So you can find some signal at quite sliced at quite apart in redshift, right? Okay.
Do we have any more questions? If not, we thank Ricardo again.
Thank you.
And we go to the next speaker, which is Felipe Oliveira, right? Okay, so we have our last speaker of the morning, is Felipe Oliveira, and he will talk about galaxy surveys in harmonic space.
Okay. Can you hear me? Okay, you can hear me. Oh, thank you very much. Sorry, because it's almost the lunchtime. I will try to not make anyone hungry or angry. So I will talk about galaxy surveys in harmonic space, and this title is kind of general because we have been doing a lot of work in harmonic space. Rogério Rosenfeld, which is my supervisor, has proposed a few works in DS. And what I about to talk is regarding the work here, the Brazilian participation group of the Dark Energy Survey, and the amazing LSS and TCP international group of the Dark Energy Survey. So, okay. It's working. Good, no problem. So I will start with a cliché, but this is our main motivation to work in this great surveys. So the universe, as we know, we are based in some hypotheses and some observations. So first, we assume that the cosmological principle is valid. So we assume that we have in large scale homogeneity and isotropy, or that we are not the center of the universe, in other words. And we also assume that the gravitational model that rules the universe is the general relativity. And we assume this because we don't have any evidence to assume other thing. It seems it works very, very well. So in the last century, we got a lot of new information about the composition of the universe. But we know that the universe is composed by a very tiny fraction of radiation, baryons, that we are pretty sure that the universe is made, but in a very low rate. And also we have the dark matter, that the first evidence was in the first middle of the 20th century, and the dark energy. So here's some of the evidence of the dark matter. We don't know exactly what is the cold dark matter or the dark matter at all, but we have a good evidence that it's. On the other hand, we have the dark energy, which the most simple way to explain is the lambda, and I'm pretty sure you all know about this. And the dark energy is responsible for a very surprising effect of the acceleration of the universe. This gave the Nobel Prize for the permuter in Rees in the 2011. And if you think the dark energy lambda is a fluid, theoretical problems. Theoretical problems, as pointed out by Zeldovt in the are related with the field theory. So we, as cosmologists, we can try to tackle those problems with another approach. We can try to falsify if the lambda exists indeed, or try to understand its nature through the observation. Here, I'm main observations. Consider here the CMB potential to make the universe flat, and CMB constrain very well the flatness of the universe. That make the universe accelerating and producing some kind of repulsive gravity. And lambda still acts in the structure formation of the universe. It slows down the structure formation and make it more consistent to what we observed. So here we will talk about baryon acoustical solutions. That is the main subject of our work in the last year. So BAO, for those new in the field, BAO is a standard statistical ruler. So can take a statistical the BAO and measure some distance. And it came from this small perturbation, the photon baryon fluid in the beginning of the universe. And after the recombination, these perturbations make an imprint in the matter clustering. It also has a very characteristic scales of 150 megaparsec. In order to study BAO, First, we will talk a bit of our modeling. We are looking in the power spectrum. Take power spectrum with this form here, and this term is for the redshift space distribution. Measure the wiggles of the provoked by the BAO using this difference here times this factor that the Gaussian damping takes in account the non-linearity in the BAO scales. We know that the non-linearity acts in very tiny scales, but we have this residual effect here. So we have our work are related to Crotty in operators, and the Crotty in Crotty at Ali, they working with this correlation in the configuration spaces. So they working with the correlation of angular and the transversal correlation function. And our proposal here was to check this in the Fourier space. So this is our basic modulation with some corrections that I will go into the details. Detecting the BAO means detecting this alpha parameter. So this alpha, the dilation parameter, it's related to the typical scales of the ring formed by the BAO. So we consider this parameterization here, and also this template for the CLs, for the angular power spectrum, which consider some modulation for the bias and some modulation for the other parameters, for noise and nonlinear residual parameters. Those that work with DS are very familiar with this. This is our BAO sample. It covers almost 1,500 degrees squared with 1.3 million galaxies divided in these 4 redshift beams, as we can see in Crotty and the Abbott and Drilica Wagner at Ali. Another important thing to do is generate some mock simulations. The mocks is what can make, we check the covariance of our data, and in order to use this, use the 1800 halogen mocks created by Santiago Avila, and Santi used the halogen, that is a code created by him, that from a single simulation, they create multiple realization that is in according to the initial simulation. We measured those 1,800 mocks using the master method, and in particular using the master by Davi Alonso. And here we can show the variations of the mocks. In the gray, the darkest gray is 1 sigma variation, and in the lightest gray is 2 sigma variation. The blue is the mean of the mocks, and the red is the theory, is the data. Which seems that work very well with the mocks. So using these mocks, we check the covariance with the covariance here is the correlation matrix, and we check the covariance with the Gaussian theory. So we can see here that the covariance is very well behaved. You can have a small deviations under the 10% for the scales that we are using. Finally, we can get to the parameter estimation. So We consider two methods here, the maximum likelihood estimator and the MCMC. So in green, we have the MCMC, and in blue, we have the maximum likelihood estimator. We have those priors here. B must be greater than 0 because B represents the bias squared. So we can see here that both methods are according very well. They agree very well. And also, we check our results in the harmonic space with the people in the configuration space. So it seems good. It seems reasonable. This line here is the standard 1 sigma standard deviation for a Gaussian likelihood, of course. And it seems very okay. Those lines here, up here, are in the case that we consider that our model has no wiggle at all. We test the case where you don't have the BAO. And they are very, very well 2 sigma. And it shows that our detection was positive. So the problem here is that everything seems pretty straightforward because we take our and they of robustness. So guys, I have to show that I've been working. So I will quickly talk about our. So for all, the original power spectrum with these modifications in the Limber approximation for small scales. Of other scenarios, our constraints seems very, very the same. S was the broadband terms. The broadband terms are those terms here, the A terms, and it can take in account not only the shot noise, that is very important in our case, but also some nonlinear residual terms. Since we don't have full control about these nonlinear residual terms, we have to try a lot of different parametrizations in order to check we are not forgetting anything in our constraints. So again, we see that our results are very consistent. We don't have much problem, just some difference here, but this is very far from 1 sigma. Other test that was done by people in the configuration space was the best number of the redshift beams. So you have to play a game here where if you put a lot of redshift beams, your alpha scattering will be low, and you do want the alpha well constrained. But on the other hand, if you put a lot of redshift beam, you have a very small number of objects in each redshift beam, and this will make your shot noise greater than you may want. So the ideal here was that we found that for redshift beams it was better because after 4 we don't have much modification, but you don't have to pay the price of having a large shot noise. Here we have the binning in the L, in the delta L. So in our case, since we are using the master approach, we have to bin in our data. And we test a number of bindings. Here we are showing just 2, but we test really a lot. And we didn't see a lot of modification in the shape of alpha or in the constraint here. We observe a little bit of modification in the goodness of fit. Other test was the cross correlation. Spoiler, the cross correlation won't change much in our constraints. So, and here we have a greater list of what we try to do in order to check the robustness of our data. And it seems everything very okay. Finally, we can compare the results in the configuration space, those 2. And in the kappa space, the fit seems very good here in the kappa, sorry, in the Fourier space. the fit seems very good. We have some problems, both for the groups, but our final result seems very good, consistent between the 3 statistics. And for a photometric survey, it seems an amazing result. We have the BAO constrained up to 0.8 in Redshift with this 4% error. This seems very good. So I will talk very shortly about our other work. We are doing the 3x2 points in harmonic space. So the idea is to reproduce what Elizabeth and the collaborator and Ali and Abbott and collaborators did in their configuration space. So we have a different selection functions for this case, optimize for this case, and we try to constrain the kappa maps and the galaxy clustering at the same time. This is a work that we have just started to do. Actually, we started before, but this last week we have very intensive sessions with some visitings here. So here I'm showing our new log normal mocks. They came from the Henrique Xavier code Flask. And we show the consistency with the theory and the mean of the data, and with each realization. This is an in the moment we are about here, but the idea is to take the catalogs in mask and DNDZ. Course, and we can generate our data vector in covariance and put this in a pipeline in order to obtain our. That time, I swear I won't enter in the details. Sorry. So our is the nature of the dark sector of the universe is still an open problem. Of course, the lambda seems a very more urgent problem than cold dark matter. We are working the harmonic space analysis, which introduces a lot of new statistics and the biases and other independent statistics from the configuration space. And we are in the road of the Y3 BAO. Our target is also implement the pipeline for 3x2 points in harmonic space, and then combine with CMB. in order to do this, we have to find a better way and effective ways to calculate the covariance. And we are looking forward for the future. We don't know what will happen. But here, those are the results of the I1 of DS. And for the people that love tension and don't love so much the lambda CDM, this seems a very promising future. I will leave you with the words of Steven Weiber. Thank you very much.
Thank you so much. Do we have questions?
Thanks for that talk. I have a quick question, which is, I know that covariance matrices have a cosmological dependence themselves. Do you know, my question is that dependence stronger in real space or harmonic space? I'm not sure if you know the answer. I'm just curious.
It's something we have to study here because we are working in this covariance, but it seems it's not very strong. But I cannot give you a definitive answer, sorry.
Any questions? I have one, actually. The power spectrum that you were using for galaxies.
Mm-hmm.
So that was the first time in front, because you were considering non-linearities, right? Exactly.
Yes.
So which is the linear one minus the no-wiggle, I guess. So, so the first time how do you name how? Which is
It's a redshift space distortion, yes.
Okay. So there's no finger of gods there.
Sorry?
Finger of gods effect.
Yes, Kaiser effect.
Okay, only.
The second, it's calibrated by simulation,
Yeah,
but
sure.
it's related for any residual of the nonlinearity that may affect those scales in the of the BAO.
And here, basically, you use as an observable, you use the photometric galaxy clustering, right?
Yes.
Not spectroscopy, because you're doing all this here. Do you have any guess? Because usually spectroscopic is somehow better now in terms of measuring redshift.
Why using spectroscopic is better?
Usually, no. I mean, usually it's better because I have a measurement of redshift which is higher, and
yes.
How this would affect, for instance, if you combine with a different survey that has spectroscopic measurements. Do you know any guess? I mean,
we have been discussing with Arthur Loureiro that is working with this combination.
Okay.
So it's not an easy task.
Okay, I imagine.
Okay, but I don't know.
It's fine. Okay, don't worry. Okay. Any questions? If not, we thank the speaker again.
Thank you very much.
It was our last speaker, so I think now we are free to have lunch, right?
So for lunch, you have a lot of two recommendations. Places here usually
So I think that the best thing to do is to meet in 10 minutes downstairs in the lobby. Okay? To meet in 10 minutes-ish in the lobby downstairs. Okay. And another thing, please, is remember to sign for the dinner if you want to participate. Thank you.